All right, class, and we're back. So here it is. Hopefully there will be audio this time. 62, state the Pauli exclusion principle in your own words. That is, in your own words, I would have to say it'd probably be something like electrons are like people, and each electron has its own address. So it would be something along the lines of, here we go, there we go. Each electron has its own address for a space outside the nucleus. Because that's really what it's like. It's like each person has an address, a state, a town, and of course your name is on that mailing address, so that's specifically to you, and that's what electrons are like. Each electron has some kind of identifier, actually four quantum numbers that describe where it is outside the nucleus. That would be the N, of course the L, the M sub L, and then the M sub S. Okay, for the major energy level, the sublevel, the orbital, and of course the spin. The Pauli exclusion principle is, in an important sense, the key to understanding the periodic table. Explain why. Well, the first main energy level only has one sublevel with one orbital, and that can hold two electrons like this. That accounts for H and HE in period 1. So the periodic table is basically set up exactly how the electrons are set up. So if the elements were electrons, the periodic table follows the electron configurations exactly. So that's that the Pauli exclusion principle is the thing that helped to determine the format of the periodic table. So as you go from left to right on the periodic table, you're increasing atomic number. You're also increasing the number of electrons in that element. And those electrons fall into place according to a pattern, and that pattern is described by the Pauli exclusion principle. So the periodic table, I should say the format of the periodic table, basically equals the electron configuration. Okay, we did the diagonal rule, but the diagonal rule is just like a simple way to be able to do it, to show the electron configuration. The periodic table actually does it, in my opinion, better. 66, what are the valence electrons? Valence electrons are two different types of electrons. There are core electrons and valence electrons. So when we're talking about like what the electrons are in aluminum, you've heard me do this one already, Z equals 13, which means 13 electrons. Okay, you know that when I write the electron configuration, I go neon like this, which means 10 electrons. Those are the core ones. They're the ones on the inside. And then after that, I'm going 3s2, 3p1. These right here are the valence electrons. They're the ones on the outside. Okay, so there's 3 valence electrons and 10 core electrons for aluminum. So what are the unpaired electrons? It's easy to see unpaired electrons. So when we're talking about aluminum has 3 valence electrons, and they kind of split themselves up like this, so these would be unpaired electrons because they are not paired. So how many valence electrons does P possess? The answer is 5, which means 1, 2, 3, 4, 5. And how many of those are unpaired? So that would be 1, 2, 3. So 5 valence electrons, 3 unpaired electrons. Okay? So let's keep moving. We're moving pretty good here. 70, in 1999, it was reported that the element 118 had been artificially made. This report was retracted in 2001 since there had been no other claims that the element 118, did I say 115? 118 had been made. Write the electron configuration for element 118. We can do this longhand or shorthand. Doesn't matter to me. For 118, we can go through this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, focus, Bensing, s2, 4d10, 5p6. Where are we at now? So 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. And that's all right there. Yeah, how many unpaired electrons would you expect to have 118 to have? 0. And to which group? It would be the noble gas group. And that's why there's 0 unpaired electrons. All right, moving on. The following electron configuration represents excited states. Excited states are when the electrons are up and not down in their ground state. So identify the element and write its ground state condensed electron configuration. Condensed is abbreviated, which is the short form. So there's 1, there's 2, 4, 6, 7. 7 is nitrogen. Nitrogen, oops, they want the condensed. He, 2s2, 2p3. And that's nitrogen. This one is argon. Argon has 18. So there's 10, 11, 15, 16 plus 18 equals, where are we at here? 34. 34 is Se. Se is argon. Where are we at here? Argon, that would be 4s2, 3d10, 4p4, like that. There we go. The next one is krypton. Krypton is what, 36? 36 electrons plus 6 plus 2 plus 1. So what is that? That's 42, 44, 45. So what is element 45? 45 is RH. RH starts off with krypton. Krypton 5s2. 4d, hang on, 4d, 1, 2, 3, 4, 5, 6, 7. 4d7. That's awful. There. 5s2, 4d7. Pretty easy. So, in case you're not sure what I'm doing, these here are the number of electrons. I count up the total number of electrons no matter where they are. That tells me the atomic number of the element. And then with the atomic number of nitrogen, then I write the condensed electron configuration with all the electrons in their ground state, or at the lowest possible energy. That's what I did for all 3 of them. Okay, moving on. Notes for the Chapter 6 test. Take a look at this. All short answers and multiple choice problems. Answer Schoology test online. Because you guys are not here, we're going to have to skip the free response part, so you will take a multiple choice and multiple choice test that will be opened up tomorrow on Friday. Only 2 to a side of the table and no codes of special periodic tables. Okay, so obviously you guys will take this test at home since we're all virtual. If you have any questions, please message me. Let me know what's going on.